So welcome back again. In the last few lectures, we were discussing about ideals, and you know that the concept of ideal is a parallel concept we have learned in group theory. That was the normal subgroups. Okay, and when we have normal subgroups, we can talk about quotient groups, and then we can study the properties. Okay, this was the scenario when we discussed the group theory. So here we have also discussed similar concept that is called the ideals. And in ideals, we have seen some classification based on one was the based on size, and that we know that we call the maximal ideal. Okay, so that okay, and another was based on the properties of element. Okay, when we say that an ideal is a prime ideal, and when we say that an ideal uh, is a maximal ideal. And you know that maximal ideal in a group in a ring may not be need not be unique. Okay, as the name suggests that maximal means that it should be maximum. But the thing is that there we may get a sequence of ideals which contain another ideal. Okay, so these are the concept we have seen in the last lectures. And now since we know what are the ideals and also some of their classifications. So now we can talk about the factor rings as we have done in group theory. Okay. But before that, let us see, I think we have seen some examples on prime ideals and maximal ideals. Okay. But still, let us have some example so that we can get uh, again some information so that we can move forward. Okay. So I was talking about maximal ideal, I think in the last lecture, or prime ideal, I don't know. Anyway, let us have some example on both. Okay. So if we have been asked that find the maximal ideal of Z8, okay. So we may try it out that what are the ideals, and then we may try it out that uh, yeah, what are the ideals, and then we may try to find out the sequence of ideals, and then we can get what is the maximal ideal. But there are some things which make life easy. Okay, so if we have been asked that this example is that uh, we have been given Z8 and find the maximal ideal. Okay, find the maximal ideal. Okay, so once you know that ideals, you can write it down. First that is I1. If I write, you know that the 0, 1 is the ideal. Okay, and then we have another ideal. I don't know if I discussed this example. uh, the ideal generated by 2, and you know that this kind of ideal, if R is a ring and A belongs to R, then this is an ideal, and this ideal is generated. This ideal generated so is given a name that is called principal ideal. You know, this is called principal ideal. Principal ideal. Principal ideal. Okay. So corresponding to each member of R, we have an ideal. Okay. So let us see. So 2 belongs to Z8. This is an ideal, and then I3 we can take. 4 is also an ideal. This generated by 4. Okay, and of course you know that they are cyclic. I3 and I4 in fact is nothing but Z8 itself. So they are the ideal. There are 4 ideals. Okay, And then as I have discussed in previous lectures, how we can find that which is the maximal ideal. Okay, so we can try to find it out that if we have uh, if you take, you know, I2, okay, that is ideal generated by 2. So this is nothing but a 2 times of Z80, you know, but a multiple of 2. So they are the same, okay. And in this we have elements 0, 2, 0, 2, 4, 4 and 8, sorry, 6. No? So they are the elements here. They are elements here in the ideal generated by 2. So this I2 is contained in, if I say, let us say I, okay, and this is contained in Z8, okay. So is there any ideal, this ideal? So because there are exactly 4 ideals there are 4 ideals are there. So can this I be sum of these? Of course, 0 cannot be this. In 4, you know that what is there? In 4, you will be getting 0, 4, only 2 elements, okay? And this I cannot take this one. I cannot be I3, you know? So either I has to be what? Z8 or I2 itself. So this implies that I2 can be, I can be I2 or I can be equals to Z8. So there is only two possibility. So certainly I2 is going to be a maximal ideal. Fine. So now question is that can we have some idea about the number of maximal ideal? Okay. So there is one formula, the number of maximal ideal ideals in Zn. So in particular case, we cannot say anything in general. Of course, if that ring becomes a field, then we can say something. If rings become integral domain, then we can say something. But in a general ring, we cannot say anything. But in some particular case, just like in Zn, we can say something. And this is equals to number of prime divisor of n. The number of prime divisors of n. Okay. So for example, just we have taken Z8, you know, in Z8, the prime divisors of 8 are prime divisors of 8 are, what are they? 2, anything else? Hello. Only 2 is the prime which divides 8. Okay. Okay. So only 2 and their number is 1. Okay. The prime are 1. And this implies that uh, only one maximal ideal, okay, of Z8. All right. So for example, if we take Z27, okay, so divisors of 27 क्या क्या होंगे इसके divisors and prime divisors prime divisors 3, what else? Hello. 3 divides 27 and then 9 divides, but 9 is not a prime, you know, 9 is not a prime. Then 3, 9, what else? So I think there is one only. Okay, rest you can find it out anyway. So next another thing is there. If we are taking R is a ring, and this is a P square Q type. Okay, this is P square Q type. Then there are how many maximal ideals are of this? Okay, so prime divisors of P square Q, according to that the above discussion, prime divisors of P square Q, P, Q are prime. Okay, they are primes. So how many? P and Q? No, only two. So maximal ideal क्या होंगे? कितने होंगे? Number of maximal ideals is going to be 2 only. Okay. Uh, so next one result I would like to mention here. Uh, that you can show that I think this may be in your exercise also. So that mz is maximal ideal of the set of integer z if and only if m equals to p, that is p is prime, p is a prime. All right. So this you can try it out to prove. Okay. So how many ideals in Z? There are infinitely many number of ideals. Okay. How many maximal ideals? Okay. And if we ask that how many ideals are there in Z, so how many? Infinitely, of course, because number of maximal ideal is going to be a subset of the total number of ideal. Okay. So many things, interesting things that we can have. So from here, we can say that 2z, no, 3z, okay, 5z, 7z, okay, are maximal are maximal ideals of z, okay, of z. So can z cannot be z 4z, no, and 6z, okay, 6z, 8z are not maximal ideals. Okay. If field has only one ideal, note one maximal ideal. Okay. A field has only one max only one maximal ideal. A few things, let us see, and then we can try to we can then see about prime. Okay, let us have similar examples in case of prime ideals. Okay, so next note, number of prime ideals in Zn. This is equals to number of prime divisors of n. In a very first glance, it seems that okay, in that case, it means that all prime ideals are maximal ideal, or maximal ideals are prime ideal. Okay, that we will see what are maximal and what are prime. Okay. So find if you have been given suppose Z16 in Z16. So divisors, prime divisors of 16 are, what are they? 2.
2.
Okay. So only one prime ideal. Okay. So in Z16, what is the prime ideal? In Z16, you know, in Z16, yeah. Do you have any idea? In fact, this is okay. And then if you next example, if we take let R be a ring, and this is ZP square Q. The similar to that to what we have taken, okay? And a P and Q are distinct prime, okay? Distinct primes. Earlier also when I have taken P square Q, it means that P and Q were distinct prime, okay? So there are all divisors of these are prime divisors are P and Q, okay? R has 2 prime ideals. And namely, what are they? P and Q. Okay. What about next example? If you take, let us say, consider the ring R equals to Z30. Okay. So prime divisors of 30 are, what are they? 3, 2 also, no? 2, 3, and 5. 3. So how many prime ideals are? 3. Number of prime ideals is 3. And namely, what are they? The ideal generated by 2, by 3, and by 5. They are. Okay. Okay, let us move further. One thing is that as we knew that the ideal intersection of ideal need not be ideal. So similar here also. Now we are taking more particular case, that is prime ideal and maximal ideal. But one thing is clear that by example, if you take that the intersection of, okay, 2 prime ideals need not be an ideal, okay? Intersection of uh, prime ideals need not be a prime ideal. Okay, intersection of prime ideals need not be ideal. And usual, the usually intersection has been, or if you take, I'm sorry, if you take in group theory, the intersection of 2 subgroups, of the same group is a subgroup, but union need not be, no? And similarly, in case of subring also, but here in case of ideal, this is a very, very different thing. Okay, just now we have seen 2Z is a prime, or we can say 3Z and 2Z are prime ideals of Z. But 2Z intersection 3Z, okay, 2Z intersection 3Z, and this is going to be equals to 6Z. No? This is going to equal to 6Z is not a prime ideal. Is not a prime ideal. Okay. Next, if I ask that every ideal is every maximal ideal in a general ring is a prime ideal or conversely, okay? So it is not true. A few things let me note down more. That every we are talking about in a general ring, every maximal ideal of R is prime ideal of R. So this is a question. Okay. So the answer is no. Okay. Need not. Need not. Okay. Need not. So you know that a 4Z is a 4Z is a maximal ideal of 2Z. Okay. 4Z is maximal ideal of 2Z. There we were talking about where we talked about that P times Z like this in here in this example. So we are talking about the ideals of this. Okay. We are not talking about the ideal of Zn. But here we are talking about, oh, sorry, 2mz. Okay. So 4Z is maximal in 2Z. Okay. But not prime. But not prime. You know, for prime, we need to see some property. If the product of 2 that is equals to 4, this belongs to 4Z, okay? But and if this belongs to 4Z, then what should be the case? Then 2 must belongs to 4Z also, okay? But 2 doesn't belongs to this 4Z, okay? That's why this is not ideal, prime ideal, okay? Next, another result, the converse part of this, every prime ideal of every prime ideal of a ring R is maximal. This is the question. So the answer is need not. Need not, okay. And then you can take the example that I equals to the singleton 0 is prime ideal in Z, but not maximal. You can get more example also. Okay, and this is a one simplest example we have. Fine. Okay, so with this with these information, let us now now one thing I would like to ask you. Can we say something about ideals in Zn? Because you know that when we were talking about when we were talking about prime ideal and maximal ideal in Zn, so what we counted a number of number of prime divisor of the integer. Okay, is Zn. Fine. So is prime ideal in Zn is the maximal ideal or what? So that you need to answer. You can answer them this question in tomorrow's class, okay? Or if you have any answer today, you can tell me. So, do you have any idea? Hello. Hello.
Yes, sir.
Do you have any idea? Any guess? नहीं, दोनों के केस में वही बन जा रहे थे ना, ठीक है. हेलो. नहीं बताएंगे। चलिए ठीक है, कल बताइएगा सोच के, है ना? Okay, so once we have information about uh, uh, what is called ideals, now let us see the factor ring. Okay, factor ring. Let R be a ring. Let R be a ring, and I is an ideal of R. Then the set, R by I, this is defined by as collection of elements of the type A plus I, where A belongs to R, forms a ring under the following operations. Okay. So in when we define a ring, okay, we need to have two operations, that is addition and multiplication. Okay. So under addition, it should be an abelian group, and under multiplication, it should be at least closed. Okay. And what else? Distribution of multiplication or addition. Na? Hello. These are the things we need to verify. Okay. So what operations are there? The operation is that if you take A and a plus in A plus I, okay, A plus I and plus B plus I, then it should be equal to A plus B plus I. Okay, so A and B should be member of R. Okay, and this is the product, and another thing what we say that sorry, this is an addition. And another thing, what is we call product should be closed, then we need to define it also. So B A plus I and B plus I, and this is equal to A times B plus I. Okay, A plus B times I, where B belongs to R. So like this, under these two operations. Okay. In your book, there is a theorem, I think 14.2. They say that existence of factor rings. Okay, existence of factor ring. That this R by I, the definition here we have defined under these two operations, forms a ring. So in that case, they are verifying that these two operations are well defined. And they say that this is a ring if and only if I is an ideal. Okay, if and only if I is an ideal. So that proof you can see. Okay, that proof you can see in your book. And for example, if you take, suppose we are taking any two elements here. Okay, we are taking any two elements. For example, let us take uh, these elements as a of course the product is all right, product is all right, because A plus B, A and B are members of R, the ring R, and therefore this is going to be belongs to the ring R itself. Okay, and this I itself. Okay, and you know that I is an ideal, so this should be necessarily going to be closed. Okay, so when you sum element of I and I, so you will be getting nothing but I only. Okay, in case of product, we can see this. We can consider A plus I and B plus I, and then we can expand it using using distribution property. So we can write it as that A AB, okay, and AI plus IB, okay, and plus I times I, it will give you I, okay, I times I, because you know that I is an ideal, so it will be closed under multiplication also. Fine. So here you see that A is element of R and here B is element of R. So it means if at all this is going to be a member of R by I, you know, if it is going to be a member of R by I, it means that this should be these all things, these two things should belongs to I, you know, and this happen in case I is an ideal, and ideal means not only if it is left ideal, you know, only this will belongs to I, and if it is right ideal, then if it is left as well as a right ideal, then in that case A I and I B both will be member of ideal, this ideal, okay, and therefore their sum also will be fine. Okay, so it means now here A, this belongs to I, belongs to I, and B iota IB belongs to I, if and only if you know that I is an ideal of the ring R. Okay. Okay. So this in that case, if I is an ideal, it means that A plus I and B plus I, this is going to be A plus B and plus I, as AI and IB belongs to I, not R, belongs to I. So there's some also. Okay. So in this is how we can say that this is a this product is well defined also if an if this I is an ideal of R. Okay. Rest for more detailed explanation, you can refer your book. Okay. Theorem number theorem number 14.2. Okay. Okay. So let us see some example so that we can understand a little bit more on this. So for example, if you take for example, if you take R as no, not this R as the ring R as the set of integer, and ideal, you know, that is 6 times Z is an ideal. Okay, of course, it's not going to be a maximal ideal. Okay, all right, but it is still an ideal. So we can talk about Ri, and this is equal to Z upon 6Z. Now, so what are the elements here? You take elements from this Z. Okay, the elements in Ri are of the form what form? A plus I, na? A plus I, and A belongs to R, like this. So we need to fix I here. So here in this case 6Z is there. Okay, 6Z is there, then another 6Z is there, like this it will go on. So from here element we start putting one element. Okay, So you know, in the set of integers, we have positive and negative number as well, both numbers. Okay. So, but let us start putting from 0, and then when one can put here 1, then 2 plus 6z, and then 3 plus 6z, you know, and 4 plus 6z. What else? 5 plus 6z. And then if you write 6 plus, if you write 6 plus 6z, if you write here 6 plus 6z, then you know that this contains all multiples of 6, and this, hello, this is also 6. So this is going to be nothing but 6z, no? Okay, this is going to be 6z itself. So it will repeat, okay, 6z, and then you can put 7 plus 6z, and then 7 plus 6z is nothing but 1 plus 6 plus 6z, and this is nothing but 6z. So we are getting here 1 plus 6z. So this element. So essentially, if you are taking positive one, then we will be getting these many elements, 6 elements. Okay, only these elements, this, and this. Okay, and after that it will repeat. And now the question is that can we put the negative also? So in that case, we can write -1 plus 6z. Okay, -1 plus 6z, and then -1 plus 6z, and then -2 plus 6z. So do you have any idea? This -2 plus 6z and -1 plus 6z, to whom they will be equal?
5 plus 6z or 4 plus 6z.
Yeah, very good. You can note down 1 point for this. 5 plus 6z. Yeah, and this is 4 plus 6z. Very good. You know, you need to see the complement then in that case. Okay, we need to see this. So exactly there will be 6 elements, and those 6 elements are very much clear. Here z by 6z, this is going to give us a 0, sorry, not 0, but 6z, no? 6z, 1 plus 6z. Okay, of course we can write 0 here. We can write 0. Let me write here. So 0 plus 6z, 1 plus 6z, and then 2 plus 6z, 3 plus 6z, 4 plus 6z, 5 plus 6z, like this. All right. Okay. So actually there are multiple of 6, 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 multiple of 6. So when we take the operation modulo 6, multiplication and addition modulo 6, so then they will be reducing to what? 0. This will be equal to 0, you know. So this z by 6z, although there the elements here are of different form. Their appearance is different, but this is isomorphic to 0, 1, 2, 3, 4, and 5, you know. And this is nothing but what? Our Z6. Okay. Hello. Are you getting what I'm trying to say? In general, if you take Z and MZ, Z and MZ, then this will be a isomorphic to, or this is equivalent to this. Okay. This will be similar to ZM. Okay. These will have we have already seen. Next example, we can take. Suppose we are taking 2z upon 4z. No? Just we have seen that 4z is maximal, no? In 2z. 4z is maximal in 2z. So what kind of elements are there? 4z we can write here. 4z again we can write here. So in 2z we have 0, and in 2z we have 2 plus, no? Like this. Okay. In 2z, there will be all multiples of 2, na? There will be multiples of 2. So here again we have 4z, na? 4 plus what? 4 plus 4z. All right. Hello. Multiples of 2.
Yes, sir.
And 6 plus 4z like this, and so on. So you know that this is completely divisible. Numbers in this set are going to be completely divisible by 4. So this is going to be 0 only. Okay, 0 plus 4z. You know, we can reduce it 4 to modulo 6, modulo 4. Here also this will be reduced to like this. So there will be only two elements, I guess. And similarly, you can take negative even numbers also. Okay, so there are only two elements. Okay, okay, fine. There are only two elements. So now, of course, we have some examples here we have taken, but now I will conclude the lecture today by putting certain questions. So questions are there are questions. So some questions like uh, when uh, when R by I, this quotient ring or factor ring, is an integral domain. When R by I is a field, okay. Uh, okay, so these there are two important questions. These need to be answered because once it is a ring, so we can obviously ask, hey, what is the condition under which this becomes an integral domain, and what is the condition under which this becomes a field? And the answer of this question, and moreover, more examples, more questions can be asked. You know, if R has unity, okay, if R has unity, can or will R by I, that is this factor ring, uh, have unity? Okay, so these are the question, and other thing also, if R is commutative, okay, then R by also commutative. So these are the questions one need to answer. Okay, so these answer to this question we will be seeing in the forthcoming classes. Okay, so let us conclude the discussion for the day. Okay.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.